Okay, next section here in Bayesian stats is entitled Algorithmic Modeling. Yeah, first off, I want to talk about something called statistical thinking. It's a bit different than programming. Statistical thinking employs a mode of thought that includes both logical and analytical reasoning. Whereas, typically when you're talking about programming, there's a lot of the logical parts, not as much of the analytic part. But the basic idea is you've got some kind of process going on, whether it's a physical process or some sort of business process, et cetera. But you've got some kind of process going on, and it has its own dynamics, and then it's going to have some variation over the top of that. Processes almost always do. And then you're going to collect data on top of that variation, and you're going to use tools on the other side of that to analyze the data. So I want to illustrate the fact that you've got process, variation, the data, and then the tools. So going from the tools down to the process, there's a few other hops in between there. And the variation part is usually what, on my data science teams, that's where the programmers usually get hung up. Because by virtue of wanting to do things logically, they don't really like to hear the notion of variance. But yet in statistics, you have to embrace that. And a lot of other disciplines too. Finance, of course, makes a very analytic view of variance. So statistical thinking, a definition here is evaluating the whole of a problem as well as its component parts, attempting to assess the effects of changing one or more variables. This approach attempts to understand not just the problems and solutions, but also the processes involved and their variances. So not just the outcomes, but also let's drill down and find out what's going on in terms of the dynamics of the processes, the root causes, and then what's the variance that we can model over the top of that. And like I said, data science is an inherently interdisciplinary field, and what I found leading data science teams is that programmers typically don't think this way. I'm a computer scientist. But when I've hired computer scientists on my teams, that was definitely something I had to take into account. On the other hand, a lot of other data scientists I know, especially a lot of notable ones, I'd say 50% of my peers in the field are coming out of physics or physical engineering, physical sciences. And there's a pretty good fit there. Okay. So having said that, I'm going to go the following few slides are based off of a paper that I have referenced a little bit later by Leah Brayman. But let's just say that we have a view of statistics where we've got some kind of input, some x coming in, and we've got a natural process, and we've got some kind of output, y. Kind of like what I'd shown before in the statistical thinking slide. In terms of stats, what we're trying to do, number one, is prediction. Predict what the responses will be for input variables in the future. So as x changes, what do you think y is going to be? And then number two, information. Extract info about the structure in the data. Be able to find associations between the x input variables and the y response variables. Or predictive variables, sorry. Okay, so getting back to statistical data modeling, here's a slightly different view of that. So instead of nature, now we've got data modeling. And let's just pick on one of them. One of my favorites to pick on is logistic regression. So many crimes have been committed in the name of logistic regression. Okay, so we've got y as a function of x, but also, as a function of some noise. And there's these model parameters that are really going to change how the data model views the world. So y is a function of those three parts. X, these are your predictive variables, these are input variables, and y, these are your response variables. And when you're working in this kind of mindset, as we mentioned before, you're really trying to optimize for the significance test, the goodness of fit, residuals, etc. That's what you're optimizing for. Not how well do you understand the relationship of y and x, but how good do your tests look? There's a great site called Laugh Out Loud Thesis, where people go and anonymously talk down their PhD dissertations. And there's some really great quips there about how much time is spent just making your test look good. Algorithmic modeling is something, this term was introduced in 2001, I believe, if not slightly earlier. But the notion there is, going back to the film Rashomon, if we've got some natural process that we admit we don't really know a lot about, but we've got some X's coming in, our inputs, and we've got some Y's coming out, we're trying to predict there. Rather than claiming, the conceit, if you will, of claiming to understand what's inside that box, let's just go ahead and say that's an unknown. But what we can do is, outside of the box, start to build up an ensemble of different kinds of models to try to explain different perspectives. So going back to Rashomon, you had 4 different points of view. You had 4 different people who were testifying in this trial about what did or didn't happen, and they all come up with a wildly different story. And it really underscores the fact that it's about perspective. It's about finding the structure in the data and having the right camera angle to be able to get zoomed in on that perspective. That's what we're trying to do, especially when we have big data. We have mountains of data. You have to be very careful being that cinematographer and zooming in just the right way to get the camera shot. That's what the computers are good for. So this view of algorithmic modeling, it wasn't trying to optimize for making the test look good. It's trying to optimize for predictive accuracy. How can you really go from the different X's changing and be able to predict the Y's? All right, so I mentioned about Leo Bremen, one of my favorite stats professors ever. I didn't take any classes from him, but just as far as the work that he's done, the papers he's written and all. In 2001, he wrote a paper called Statistical Modeling, the Two Cultures. And this is when he was a stats prof at Berkeley. And this paper really kind of chronicled a sea change. Because you think about it, 2001, we'd started to have some early successes in big data. We'd had, definitely Amazon and Google was coming up in the ranks, and Yahoo Search, eBay. We had other types of companies that were really making something out of big data, and they were doing it in a way that was very different than what previous companies had done, and a lot of it had to do with how they were handling their data. So Bremen was chronicling this kind of sea change away from, say, what the insurance firms and the big pharma companies were doing with their, actuary tables or drug trials or whatever. Instead of that kind of siloed manual process, making judgments in isolation, making the test look good, instead you had these newer companies coming along, handling, mountains of data, throwing thousands of servers and clusters at them, and they were using a different approach called algorithmic modeling. That's what Bremen called it. So in 2001, he chronicled this, and he started talking about how people were using machine data, the log files coming off of your web apps, capturing social interactions, how they're using machine learning, how they're using automation to kind of get this feedback loop from your log files back to make the web app smarter, and correspondingly, this sort of shift to having interdisciplinary teams, what we call data science. For what it's worth, data science, a lot of people say that it really didn't come into usage until, 2008 or 9. You can find some literature about data science rolling back many years earlier out of Bell Labs, where they were trying to suggest curricula changes in the universities, but they didn't really do much with it. So, interdisciplinary teams, algorithmic modeling, one of the technologies that emerged about the same time, in fact, Bremen was one of the authors of something called random forest, which is a kind of ensemble, bagging, bootstrap aggregation. So these are the highlights, but I'll just read the quote. A new research community using these tools sprang up. Their goal was predictive accuracy. The community consisted of young computer scientists, physicists, and engineers, plus a few aging statisticians. He's talking about himself. They began using the new tools and working on complex prediction problems where it was obvious that data models were not applicable. Speech recognition, image recognition, nonlinear time series predictions, handwriting recognition, prediction in future financial markets, and as well, eBay doing what it was doing with auctions and Google doing what it was doing with search, and Amazon doing what it was doing with product recommendations, etc. All right, so talking about ensembles, I think this is a really crucial point. Brayman refers to these as a multiplicity of data models. And remember, this gets back to Rashomon. You've got something that happened, and the critical part is how can you get the right camera angle on it? How can you get the right POV? Because if you have 4 people looking at something that happened, you're going to come out with 4 wildly different stories. What Brayman was saying was, rather than focus on having a single data model and throwing the data away and just focusing on that data model and how good your tests look, instead, why not have a lot of data models? Why not have a bunch of cameras all around the scene of the crime? And then you can switch perspectives to zoom in on what it is that really matters. So that's ensembles in a nutshell. And it's interesting because the Netflix prize happened, a few years after that. But when you look at the winning teams out of the Netflix prize in both years, particularly there's a great quote here from the Belcourt team. I believe it was the 2007 prize. They didn't use just one data model. They ended up using over 100 for their winning approach. And then when you look at the next year, all these teams are using a lot of models. As you got closer and closer to the end of the prize, the teams themselves started to coalesce into ensembles. So you get these, super groups of, a bunch of teams put together, and they all had a lot of different models. And that kind of multiplicity is what it took to win the Netflix prize. A great quote, while in the process of combining models adds complexity, making it more difficult to anticipate or explain predictions, accuracy may substantially increase. Okay, so ensembles are going to make it a lot harder to reverse engineer, where the prediction had come from, but it does increase the accuracy quite a lot. There's a couple of great presentations, papers, etc., however you want to call these, but Todd Holloway and Lester Mackey were both competitors in the Netflix prize. Todd Holloway had one called Ensemble Learning, Better Predictions Through Diversity. And Lester Mackey has one, The Story of the Netflix Prize and Ensembler's Tale. I've got the links for both of those, highly recommended. These days, Netflix isn't doing the Netflix Prize. There's the Kaggle competition, other kinds of competitions like Marine Explorer, etc. But you do see embracing this diversity of models by using ensembles. Okay, so computational thinking. Let's take a look at the big picture. Somewhere in the late 1990s, a handful of very smart people began to automate the process of making educated guesses based on large amounts of data. And rather than isolating factors or isolating hypotheses, they did it differently. And the change was they leveraged algorithmic modeling. They leveraged machine learning. They leveraged ensembles, etc. The results became actionable insights in e-commerce, catalog, auction, search, ads, etc. Some of those entrepreneurs, of course, made a lot of money off of it. Bezos, Omidyar, Brand Page, etc. But the long and the short was it really gave us a much better way to grapple with understanding what is the structure of a big amount of data and what is the POV that we need to get the right insights to take action on that. And that's what we're trying to do. Okay, in terms of computational thinking, I'd like to highlight about algorithm design. Instead of making the data fit a particular model, instead we build ensembles to describe the structure of the data. So, rather than trying to push everything, shoehorn it in, we're actually trying to take a multiplicity of different models and apply it to capture a lot of different patterns, a lot of different nuances. You can think of algorithmic modeling being much like a cinematographer, again, trying to get the right camera angle for an important scene of a film. And so we want to leverage computation to obtain the most important perspective. Taking this a little bit further, looking ahead, when we consider the notion of data workflows in the context of Bayesian approaches, it's very interesting. And again, taking into account algorithmic modeling and ensembles and all this, I will point to a couple of resources that I'd recommend from a couple of great authors regarding something called probabilistic programming. One is Bo Cronin. He had a great talk at Strata Santa Clara this year. And I've got the link there for his talk. Probabilistic programming, why, what, how, and when. And also, excellent series of blog posts by Rob Zinkov called Convex Optimized. There's one in particular called Why Probabilistic Programming Matters. Again, if you take this notion of enterprise data workflows and you really take a look at what's happening in terms of making judgments over time as things are changing, using more of a Bayesian perspective, start to put all the pieces together of what we've learned since 1997, probabilistic programming is the direction that we're heading.